Hi everybody. So I am faculty from Giraj Government College, Nizamabad. So Department of Mathematics. So our topic is BSC third year Mathematics. In that vector space in dimension of vector space and rank of matrix. So dimension of vector space and rank of matrix is our topic. So first, what is the dimension of vector space? So what is the dimension of vector space? So before going to the dimension of vector space, so we discuss basis of vector space. So what is the basis of vector space? So basis of vector space is, so B is non-empty subset of vector space V, and B is linear independent V equal to span of B. Then we say that B is basis for vector space V. So here if B is basis for vector space V, then total number of elements in basis set is called dimension of vector space. So dimension of vector space is the total number of elements in basis set is called a dimension of vector space. So the dimension of vector space V is defined as the total number of vectors in a basis of V, and it is denoted by dimension V. So dimension V means total number of elements in basis of vector space. So a vector space V is called finite dimensional if it has a basis containing a finite number of elements. And if a vector space V is not finite dimensional, then it is called infinite dimensional vector space. So the dimension of vector space is finite, then we say that it is finite dimensional vector space. Means total number of elements in basis set is finite, then those vector space is called a finite dimensional vector space. So if it is not finite dimensional vector space, then it is called a infinite dimensional vector space. So it is the definition. So now some note is there. So here R to the power n is called a n-dimensional vector space, and dimension of R equal to n. So here R to the power n means that set contains n ordered elements, say v1, v2, so on e vn. So it is n-dimensional vector space. Next, Pn is called a polynomial vector space. So what is the dimension of Pn? Means n plus 1. So Pn means it is nth degree polynomials, set of all nth degree polynomials in X. So its dimension is the n plus 1. So next, singleton 0 is called a zero dimensional vector space, or it is also called a null space, and dimension is the 0. If dimension is 0, then that vector space is called zero dimensional vector space or null space. So here standard basis of R to the power n has n vectors, e1, e2, so on en, and standard basis of Pn has n plus 1 vectors, because here in the polynomials constant value also there. So 1x, x square, so on, x to the power n. So now the problem. So find a basis for the subspace and state the dimension. So basis for the subspace. So basis for the subspace means, so first given problem is, so s minus 2t, s plus t, 3t. So here we write x, and two variables are given, s comma t are two variables. So we write s into its coefficient values, so 1 1 0, plus t into its coefficient values minus 2 1 3. Means, so elements of given set, we write linear combination of two vectors, say v1 and v2. So v1 is 1 0 0, v2 is minus 2 1 3. So here h equal to span of v1 v2. So h equal to span of v1 v2, and we know span set is subspace. So we say that h is span of v1 v2, h is subspace. So h is subspace. So here v1 v2 are not multiples of each other. These two are different vectors. Different vectors means these two vectors are linear independent, and these linear independent vectors form basis for H. So what is dimension of H? Dimension of H is the 2 here. So first elements of H we write a linear combination of the vectors, and those vectors are different vectors means linear independent vectors, and those vectors form basis for H. So we say that dimension of H is 2. So next problem. So here the problem is 2a minus 4b minus 2a. So how many variables are given? A comma b are two variables. So here we write a into its coefficients. So a into 2 0 minus 2 plus b into its coefficients 0 minus 4 0. So here the vector of given set is linear combination of two vectors v1 comma v2. So these two vectors are different vectors. So there is no scalar multiple of another. Means these two vectors are different vectors. So we say that these two vectors form. So these two vectors form basis for the vector space. So dimension of vector space is 2. In the third problem, so here the given vector is the form 2c, a minus b, b minus 3c, a plus 2b. So here three variables are there, a comma b comma c are three real numbers. So we write those three variables coefficient values from the vector. So 0 1 0 1, 0 minus 1 1 2, 2 0 minus 3 0. So here also, so given vector is linear combination of these three vectors, and these three vectors are different vectors. So we say that these three vectors are linear independent and they form basis for given set. So therefore, what is the dimension? Dimension is 3. So in the next problem, find a basis for the subspace and state the dimension. So here the problem elements a, b, c such that a minus 3b plus c equal to 0, one equation, b minus 2c equals 0, second equation, 2b minus c equal to 0, third equation. So here vector is the form ABC, and ABC are satisfies these conditions. So from these conditions we write in matrix form. From these conditions, three conditions we write in matrix form. So that form is Ax equal to 0 bar. That form is Ax equal to 0 bar. So that form is Ax equal to 0 bar. That form is Ax equal to 0 bar. In that, matrix A is reduced to upper triangular form by using row operations. Again we write equations, or in the upper triangular form we define pivot columns. So number of pivot columns equal to number of rows of matrix. Then we say that matrix are given vectors form linear independent. So here the matrix is 1 minus 2 1. So 0 1 minus 2, 0 2 minus 1. So this matrix reduced to upper triangular form. So means we want to first row first element 1, and we make by using that one we make below diagonal elements are zeros. So already zeros are there. So next we want second row second element 1. So by using 1, that one we make below values are zeros. So below values are zeros, then we obtain the matrix 1 0 minus 5 0 1 minus 2 0 0 1. So here it is the upper triangular form. So it is upper triangular matrix, below diagonal elements are zeros and diagonal values are 1 1 1. So what are the pivot columns here? First column, second column, third columns are pivot columns. Number of pivot columns 3 and number of rows also 3. So these three pivot columns form basis for given set. So therefore, what is the dimension here? Dimension is So here matrix A is this one. So det not equal to 0. So here we write equations A into 1 into A equals 0, 1 into B equals 0, 1 into C equals 0. So the only solution to this system is the trivial solution. So therefore the only element of the set is 0 vector. So this means the set is 0 dimensional and there is no basis. So second problem. So A, B, C, D such that A minus 3B plus C equal to 0. A, B, C, D such that A minus 3B plus C equal to 0. So here we write one equation or A equal to 3B plus C. That value we write in A, B, C, D. So here A, B, C, D, A value we write, we get vector in 3 variables B, C, D. So we write B coefficients and C coefficients and D coefficients. So it is linear combination, A, B, C, D is linear combination of 3 vectors V1, V2, V3. So vectors are 3, 1, 0, 0, minus 1, 0, 1, 0, 0, 0, 1. So what is the dimension here? Dimension of G is vector space is 3. So next one problem. Find the dimension of the subspace of all vectors in R3 whose first and third entries are equal. First and third entries are equal. So it is R3 means it contains in the vector 3 ordinates. So first and last vectors are equal. So the vector is the form ABA. ABA means here two variables are there, A comma B. We write A into 1 0 1 plus B into 0 1 0. So here two vectors 1 0 1 0 1 0 form basis element. These two are linear independent vectors and these two vectors form basis. So therefore dimension of H is 2. So therefore dimension of H is 2. So next problem, find the dimension of the subspace H equal to A minus 3B plus 6C. So 5A plus 4D, B minus 2C minus D, 5D. So here how many variables are there? 4 variables are there. A, B, C, D. So here we get 4 vectors. So 1 5 0 0 minus 3 0 1 0 6 0 minus 2 0 0 4 minus 1 5. So now we check these 4 vectors are linear independent or not. So linear independent means these 4 vectors are different. If any one vector is linear combination of the remaining or another, then we say that those vectors are linear dependent. So now here we check V2 and V3 relation. V2 and V3 relation. V3 is linear combination of V2. V3 value we write 2 minus 2 V2 minus 2 V2 minus 2 V2 is we get V3. So V3 is linear combination of V2 means V3 is LD vector. So remaining 3 vectors V1, V2, V4 form basis for V1, V2, V4 form basis for given set. So here dimension H is 3. So it is one method. Another method is, so these 4 vectors we reduce to upper triangular form. In the upper triangular form, pivot columns form basis. So next problem, find a dimension of the subspace spanned by the given vectors. So 1 minus 5 minus 2 10 minus 3 15. So given 3 vectors we write in matrix. That matrix is reduced to upper triangular form. So in the upper triangular form, pivot columns form basis and those columns are linear independent. Non-pivot columns are not to form basis and those columns are called free columns. So here matrix A is reduced to upper triangular form. Then we obtain the matrix 1 minus 2, 1 minus 2 minus 3. So here three columns are there, 1 0 minus 2 0 minus 3 0. So here 1 0, first column is pivot, second third columns are linear combination of first column, second third columns are linear combination of first column, minus 2 into 1 minus 3 into 1, it is the linear combination. So these two columns are non-pivot columns. So here first column means first vector form basis for H. First column means first vector form basis for H. So what is the dimension of H here? 1 is the dimension of the H. So next problem. So 1 0 2 3 1 1 minus 2 minus 1 1 5 2 2. So first we write these vectors in matrix form, and we make these vectors in matrix form, and that matrix is reduced to upper triangular form, and we write pivot columns. So pivot columns form basis for the given vector space. So matrix form here we get so 1 0 minus 3 2 0 1 4 minus 3 0 0 0. So here we get two pivot columns, first column and second column. Third, fourth columns are free columns. Are these two columns linear combination of the first and second? Minus 3 into 1 plus 4 into 1. 2 into 1 minus 3 into 1 means first, second are pivot columns, third, fourth are non-pivot columns. So first, second columns or first, second vectors form basis for the vector space. So we say that dimension of the vector space is 2. So in the next problem, 1 minus 2 0 minus 3 minus 6 0. So minus 2 3 5 minus 3 5 5. So here these vectors reduced to upper triangular form, then we get the form is 1 0 0 0 1 0 7 5 0 0 0 1. So here how many pivot columns are there? First column, second column, third columns are pivot columns. So remaining first, second, fourth columns are pivot, third is free column. So first vector, second vector, fourth vector form basis for the given vector space, and dimension is the 3. So now dimension of null A and column A. So definition of dimension of null A and column A. So the dimension of null A is the number of free variables in the equation Ax equal to 0 bar, and the dimension of column A is the number of pivot columns in capital A. Suppose here Ax equal to 0 bar is the equation. It is called homogeneous equation. In that matrix A is reduced to upper triangular form, means matrix A we write in echelon form. In that form, pivot columns form basis for column A, and non-pivot columns form basis for null A. So now in the example, find the dimension of the null space and the column space of the matrix. We want a dimension of the null space and dimension of the column space of the matrix. So first A matrix is given. So that matrix is reduced to upper triangular form, or we say that echelon form. So that form is 1 minus 2 2 3 minus 1 0 1 0 0 1 2 minus 2 0 0. Last row elements are zeros. Here how many pivot columns are there? So first column is the pivot column, second one is linear combination of first one, means it is non-pivot. Third column is the pivot column, and fourth, fifth are linear combination of third. So we say that these two are free columns. So now what are the here pivot columns? First, third column. So these two column vectors, first, third column, vectors form basis for the given set. So third third columns are pivot columns. So these two vectors called dimension of column A. Non-pivot columns form dimension of null A. So here there are three free variables. Free variables means second, fourth, fifth. Second, fourth, fifth means dimension of null A is 3 and dimension of column A. First, third columns are pivot columns. So dimension of column A 2 and dimension of null A is 3. So here determine the dimension of null A and column A for the following matrices. So determine the dimension of null A and column A for the following matrices means. So first matrix A is given. So here direct upper triangular matrix is given. Matrix A is upper triangular matrix is given. So in that, so which columns are pivot columns, which are non-pivot columns, we verify. So first column is pivot. So second column is pivot. Third one is second, third same model means it is linear combination. So next fourth column is pivot and fourth and fifth are linear combinations means which are pivot here first, second, fourth. First, second, fourth form basis for column A. Basis for column A means dimension of column A is 3. Remaining two columns are basis for null A, now free columns. So here free columns are third and fifth. So these two columns form basis for null A. So dimension of null A 2 and dimension of column A 3. So in the next problem, 1, 2, minus 4, 3, minus 2, 6, 0. First row element, second row 0, 0, 0, 1, 0, minus 3, 7. Next third row, fourth row is given. So in this, so we check which are pivot, which are non-pivot. First column is pivot, second is linear combination of first one, second, third are linear combination of first one means these two free columns. Next fourth column is pivot, fifth one is pivot. So here sixth, seventh columns are linear combination of first, fourth, fifth means these two are free columns. So here which are pivot? First, fourth, fifth. Remaining are free. So four pivot columns are there. Dimension column A 4 and 3 non-pivot there. Dimension of null A is 3. So in the next problem, A equal to 3, 4, minus 6, 10. So matrix A is reduced to upper triangular form. Then we get 1, 0, 0, 1. So two pivot columns are there. So these two columns, first, second columns form basis for the vector space and dimension is 2. So here we have theorems, some theorems are there. So first theorem, if a vector space V has basis B, B1, B2, so on Bn, then any set in V containing more than n vectors must be linear dependent. So B has n linear independent vectors and so here if a vector space V has a basis B, B1, B2, so on Bn. So any set in V contain more than n vectors must be linear dependent. So here first let U1, U2, so on UP, U1, U2, so on UP be set in V with more than n vectors. The coordinate vectors are U1 of B, so on UP of B form linear dependent. We will take linear dependent vectors. So because there are more vectors of P. So P greater than n means these vectors are linear dependent. So in each we write a linear combination of the coordinate vectors C1 into U1 of B plus so on Cp into UP of B equal to 0 vector. Next we write definition. So box of coordinate matrix of u1 u2 so on up equal to 0 bar. Here we equate, so we get the equation c1 u1 plus c2 u2 plus so on cp up equal to 0 bar. So we get c1 c2 so on cp equal to 0. So one c1 c2 so on cp equal to 0. So here, so we say that these vectors are linear independent. Here we get, but we will take linear dependent vectors. Linear dependent vectors means in the c1 c2 so on cp any one scalar value not equal 0, but here we get all values are zeros means linear independent. So therefore we say that our assumption is wrong. So therefore b is therefore vector space B has basis B, b1, b2 so on bn. Then each linear independent set in V has no more than n vectors, means it contains only n vectors, n Li vectors. Then they form basis for V. So now the next theorem is, next one theorem is there. So the theorem, so if a vector space V has a basis of n vectors, then every basis of V must consist exactly n vectors. Means every basis of V has exactly n vectors or same number of vectors. Exactly n vectors or same number of vectors. So means here we define two bases for V. So we show that those two bases contain same number of elements. So first B1 has a basis of n vectors and B2 be any other basis of V. So here B1 is basis and B2 is linear independent. Both are basis. So here B has n elements and B2 is another basis. So here we will take B1 is basis and B2 is linear independent. So B2 has no more than n vectors by the theorem, then B2 is linear dependent set. So here, so by 9 also B2 is basis. So here B2 is linear independent. B2 has no more than n vectors by the theorem 9. So also if B2 is basis and B1 is linear independent, same way we apply. So B2 has compulsory n vectors. So thus B2 consists of exactly n vectors. So therefore both the bases of vector space have the same number of elements or number of vectors. So next one theorem, basis theorem. So this basis theorem is statement. So let V be a p-dimensional vector space p greater than or equal to 1. Any linear independent set of exactly p elements in V is automatically a basis for V, or any set of exactly p elements that spans V is automatically a basis for V. So it is the basis theorem statement. So here the proof is, so by the previous theorem, so every basis of V contains exactly n vectors and linear independent set also contains exactly n vectors. So here a linear independent set S of P elements can be extended to form basis for V. So here S set has P elements, and S is linear independent, then directly we say that S is basis for V. So if S has less than elements, then we check it is basis or not. So here, so first linear independent set S of P elements can be extended to basis for V. So but basis must contain exactly P elements, since dimension of V equal to P. So dimension definition is total number of elements in basis of vector space. So here dimension of P equal to dimension V equal to P given means every basis of V contains exactly P elements. So must already be a basis for V. So dimension V equal to P and S set contains P elements. So S is linear independent means S is basis for V in the first case. So now next step. Now suppose that S has P elements and spans V. Since V is non-zero, The spanning set theorem implies that a subset S dash of S is a basis of V. So since dimension V equal to P, S dash must contain P vectors. So therefore S equal to S dash. So therefore we say that S is by spanning set theorem, S also basis of V. So here the next theorem. So let H be subspace of finite dimensional vector space V. Any linear independent set in H can be extended if necessary to a basis for H. Also H is finite dimensional and dimension H less than or equal to dimension V. So first we will take H equal to singleton 0. Then certainly dimension H equal to 0 less than or equal to dimension V. Otherwise, so here if H equals singleton 0, then dimension H value 0. That is less than or equal to dimension V. So in the first case H equal to singleton 0 bar, then theorem is proved. Second case H not equal to singleton 0 bar. Then here we define S equal to U1, U2, so on, UKB linear independent set in H. Here if S spans H, then direct we say that S is basis for H. So if S is not span for H, then otherwise there is some vector UK plus 1 in H and that is not in the span S, then U1, U2, so on, UK plus 1 is linear independent. So because no vector in the set can be linear combination of its preceding vectors, then those vectors form linear independent. So long as the new set does not span H, okay, so we can continue this process of expanding S to larger linear independent set in H. But the number of vectors in linear independent expanses S can never exceed the dimension of V by the theorem 9. So eventually the expression of S will be span H and hence will be a basis for H, and dimension H is less than or equal to dimension V. So here next one, another one definition, row space. So what is a row space? So if A is an m by n matrix, each row of A has n entries and thus can be identified with a vector in R to the power n. So the set of all linear combination of the row vectors is called a row space. So the set of all linear combinations of the row vectors is called the row space of A and is denoted by row A. So each row has n entries. So row A is subspace of R to the power n. Since the rows of A are identified with the column of A transpose, we conclude also write column A transpose in place of row A. That is row A equal to we write column A transpose. Row A equal to we write column A transpose. So here if two matrices A and B are row equivalent, then their row space are the same. If B is in echelon form and the non-zero rows of B form basis for the rows of A as well as for that of B. So if B is in echelon form, the non-zero rows of B form basis for row space. So now here the problem. So find the basis for row space, column space and null space. So first A equal to given. So 2 minus 5 8 0 minus 17 1 3 minus 5 1 5 3 11 minus 19 7 1 1 7 minus 13 5 minus 3. So to find a basis for the row space and the column space, row reduced to A to an echelon form. So first in the matrix A, that one is reduced to upper triangular form, means echelon form. So here the echelon form is 1 3 minus 5 1 5 0 1 minus 2 2 minus 7 0 0 0 minus 4 20. So last row elements are zeros. In this pivot columns form basis for column space. Non-pivot columns form basis for null space. So non-zero columns form basis for row A. So here first by the theorem, which are pivot columns? First, second, fourth. First, second, fourth are pivot columns. So these three columns form basis for column space. So by the theorem, the first three rows of B form basis for the row space, not first three. So as well as so first basis for row. Okay. So in the echelon form, non-zero rows form. In the echelon form, non-zero rows form basis for row space. So first in the echelon form, non-zero rows form basis for row space. So in echelon form, pivot columns form basis for column space. Non-pivot columns form basis for null space. So here number of non-zero rows, first, second, third are number of non-zero rows. These three rows form basis for row space. Okay, 1 3 minus 5 1 5, 0 1 minus 2 2 minus 7 0 0 0 minus 4 0 20. So these three. Next, for the column space, observe that from B that the pivots are in the column first, second, fourth columns are pivot columns. So these three columns these three column vectors form basis for column A. So next, so non-pivot columns. So non-pivot columns form basis for null A. So non-pivot columns basis for null A elements. Here B matrix, from B matrix we write equations. Those equations are we write x1 x2 so on, and we write in X matrix form. So we write linear combination vectors form basis for null A. So here basis for null A is 2. So same model problem here. So assuming that the matrix A is row equivalent to B without calculation. So list rank A and dimension null A, then find the basis for column A, row A and null A. So first column A. So first A and B matrix are given. So B is row equivalent to A, means B is upper triangular matrix. So from B we will take all definitions. So in the B, first non-zero rows form basis for row A. Non-zero rows form basis for row A. So next, second, so pivot columns form basis for column A. So non-pivot columns form basis for null A. So how many non-zero rows are there in B? So first, second rows are non-zero rows. These two rows form basis for row space, means rank is 2. Next, here pivot columns. First, second columns are pivot columns. So these two column vectors form basis for column A. So remaining third, fourth columns are non-pivot, and these two vectors form basis for null A. So same second problem, same model. So here check third one. So in the third, A is equivalent to row equivalent to B. Equivalent means both the matrices are same. So B is upper triangular form matrix of A or echelon form matrix of A. So here non-zero rows, first in B, first, second, third rows are non-zero rows. These three rows form basis for row space, So next, pivot columns, first column, second column, fifth column are pivot columns. So these three columns vectors form basis for column A. So from B, write Bx equal to 0 and write equations. Those equations solved for x1, x2 so on values. Next write X, from X linear combination vectors form basis for null A. So here null A values 3 by 2, 1, 0, 0, 0, 9 by 2, 0, minus 4 by 3, minus 3, 1. Similar fourth problem. So here rank and nullity. So the definition, rank and nullity. What is rank? What is nullity? Rank definition: the dimension of column space of A is called the rank of A. So the dimension of column space of A is called the rank of A. So row A equal to column A transpose, and the dimension of the row space of A is the rank of A transpose. Means A and A transpose ranks are equal. So row A equal to column A transpose. The pivot columns of matrix A form basis for column A, and total number of pivot columns is rank of matrix. So here in the matrix A echelon form, so pivot columns form basis for column A, and the total number of pivot columns is called rank of the matrix. Nullity. So the dimension of null space of A is called nullity of A. The dimension of null space of A is called nullity of A. The free columns of matrix A for form basis for null A, and total number of free columns is nullity of matrix. So total number of free columns is nullity of matrix. So rank is number of pivot columns is called rank of matrix. So number of non-pivot columns called nullity of matrix. So here one theorem statement only, invertible matrix theorem. So what is the statement of invertible matrix theorem? Means let A be an n by n matrix, then the following statements are each equivalent to the statement that A is an invertible matrix. So first statement, the column of A form basis for r to the power n, column A equal to r to the power n, dimension of column A equal to n, rank of A equal to n, null A equal to singleton 0 bar, dimension null A equal to 0. So the rank theorem. So the rank theorem, so it is the important theorem. So rank theorem statement is the dimension of the column space and the row space of an m by n matrix capital A are equal. This common dimension, the rank of A, also equal the number of the pivot columns in A and satisfies the equation rank A plus dimension A equal dimension null A equal to n. Rank A plus dimension null A equal to n. In the proof, first let A be m by n matrix. The pivot columns of matrix A form basis for column A, and total number of pivot columns is rank of matrix A, and matrix A is equivalent to B. So rank A is number of pivot positions in an echelon form of B of A. So number of pivot columns in echelon form B of A is called rank, and the rank is also the dimension of the row space. So the dimension of null A is the total number of free columns in the equation Ax equal to 0. So therefore we say that number of pivot columns plus number of non-pivot columns equal to number of columns in A. So number of pivot columns is, we say that rank of A. Number of non-pivot columns is, we say that dimension of null A. Total number of columns in the matrix is n. So the theorem is proved. So one problem. So if A is 7 by n matrix with a two-dimensional null space, what is the rank of A? So since A has n columns, rank A plus 2 equal to n, then hence rank A equal to 7. 9 minus 2, 7. Next, could 6 by 9 matrix have two-dimensional null space? So no. So if 6 by 9 matrix call it B had two-dimensional null space, it would have to rank 7 by the rank theorem. So here 7 minus 9 means here we get 2, but here we want 1. So but the column of B are vectors in R6, and so the dimension of column B cannot exceed 6. So that is rank B cannot exceed 6. So here the next problem. So if 7 by 5 matrix A has rank 2, find the dimension null A, dimension row A, and rank A transpose. So A is 7 by 5 matrix, means n equal to 5. So rank is 2. Rank is 2 means 5 minus 2, 3. So it is dimension null A. So dimension row A equal to rank of A, it is 2. Rank A transpose equal to dimension A transpose equal to rank A, both are same. So it is 2. So namaskar to everyone. So thank you. ధన్యవాదములు.